Okay, so welcome to the last video on correspondence theory for modal logic. And what I want to do in this video is just wrap up and say some general comments about correspondence theory. So I'm going to start with a common mistake. And this is, you might be tempted to think that this statement is true, but I'm going to explain to you why it's not. So I don't want you to fall into a common trap that common mistake that beginners often make. So we've shown that for any frame, the frame F validates box phi implies phi if and only if the frame F is reflexive. That's what we've shown. So we've shown that for any frame, if box phi implies phi is valid, then the frame is reflexive, and vice versa. If the frame is reflexive, then box phi implies phi is valid. So you may wonder, does the same hold? Why do we have to do that for frames? Does the same hold for models? And so it's actually relatively instructive to see why this is not true. So it's not the case that for any model, if box phi implies phi is valid on that model, that's true just in case, or if and only if the relation in which that model is based on is reflexive. So, and to see, let's look at an example to see why this is not true. Consider the following model. There's a state W that can see a state V. Now, let's just make P true at the state V. Okay, now we can see that, and the state W. Let's just make P true both at W and V. Okay, now on this model, so this is our model M. On this model, it's valid that box P implies P. So box P implies P is valid. So it's true at state W. It's also true at state V. So box P implies P is going to be valid on this model, but it's valid for a trivial reason. It's valid because of the particular valuation for P. If I found another model based on the exact same frame, so you have W and you have V, another model, I could find another model in which, for example, we have a different valuation in which P is true only at V. And in this model, M prime, we have M prime does not satisfy box P implies P, because box P is true at state W, but P is not true at state W. We do have M prime at state V that box P implies P is true at state V. Again, that's just for a trivial reason because P is true, so the implication is immediately true. So we can see what's the situation. We have a model here. The relation is not reflexive, but box P implies P happens to be valid. So it's really important, the fact that I phrase this, the original result is that for any frame, the frame validates the formula box phi implies phi if and only if F is reflexive. So it's important that this is a fact at the level of frames and not at the level of models, because when you fix a particular model, you fixed a valuation. And so it might be just for trivial reasons, just because the valuation happens to make P true at all of the states, that a formula like box P implies P happens to be true everywhere in the model. And in fact, we could just have all the atomic propositions be true everywhere, then box P, no matter which atomic proposition you pick, that'll be true. So it's important that when we say that this formula box phi implies phi is valid on the frame, that you quantify not just over all states in a particular model, but all possible valuations, all ways of interpreting this formula phi. So in fact, this correspondence statement saying that a formula is valid on a frame is really a second order statement, because you're quantifying over all possible subsets of the model that you could assign to a particular atomic proposition. So it's really a second order statement, and what's really, really amazing about modal logic, about correspondence theory, is that some modal formulas correspond, in fact, to very simple first order formulas. You can kind of remove that second order quantification. Okay, so this is just a common mistake. It's a mistake that many people make initially when you first learn about correspondence theory. So I wanted to flag this so that you know that the corresponding statement about models is just not true. Okay, now I just want to end with a few general comments about correspondence theory. So first of all, not unlike what I've shown you thus far, not all first order properties have corresponding modal formulas. So in particular, the first order formula corresponding to what it means to be irreflexive. So for all states W, it's not the case that W is related to itself. So for all states in the model, we know that there are no reflexive arrows anywhere in the model. That is a first order statement. We can impose that. We can look at the class of all frames that are irreflexive. You can prove that you can't find a modal formula that corresponds to this property of being irreflexive. I'm not going to sketch that proof here because you need a bit more machinery. You need a bit more machinery about the model theory of modal logic to prove it. But it's important when you introduce correspondence theory to just help you understand the limits, what can be proved and what cannot be proved. So it's not the case that all first order properties have corresponding modal formulas. The sort of converse of that is it's not even the case that all modal formulas correspond to first order properties. So in the previous slide, I said that correspondence theory is when we say that a modal formula is valid on a frame, that's really a second order statement. You're really quantifying, and it's important that you're quantifying over all possible valuations. And quantifying over all possible valuations is like a second order quantifier because you're quantifying over all possible subsets, all possible ways of assigning subsets to atomic propositions. And here are two classic examples. And again, I'm not going to go through these proofs because they're a bit more sophisticated, but this is called the Gödel-Loeb axiom. Box phi implies box phi. That corresponds to the frame being transitive and converse well-founded. So converse well-founded, well-founded means there's no infinite descending chains. Converse well-founded means as you're going, you're looking at the opposite direction of the relation. But it's well known that well-foundedness is not a property that can be expressed in first order logic. So modal logic, in this sense, modal logic goes beyond first order logic. You can express things at the level of frames that go beyond first order logic. It's also known that this formula, box diamond implies diamond box, this is called the Mckinsey Axiom. This does not correspond to any first order condition. It corresponds to some second order condition. It's complicated to write down. Interestingly, the converse of this, diamond box phi implies box diamond phi, that does in fact correspond to a relatively simple first order formula. And I'll leave it as an exercise for you. Figure out what that first order formula is. What first order statement does diamond box phi implies box diamond phi? What does that correspond to? And finally, I should mention, I'm not even going to be able to discuss the details of this at all, but I'll refer to this book, Modal Logic by Blackburn, De Rijke, and Venema for a discussion of this. Sahlqvist axiom. This is a general axiom general algorithm such that if you give me any modal formula that satisfies a particular shape, so it's not any modal formula, but it's modal formulas that are of a certain form, that has a certain syntactic shape. So for a so-called Sahlqvist formula, there's an algorithm that will automatically calculate or determine what is the first order property that corresponds to this modal formula. And it's quite general. It covers all of the most of the axioms that you'll come across doing sort of working with simple modal logics, like many of the ones you'll find when studying philosophical applications. So Salkvist's algorithm is a very powerful algorithm, and again, it doesn't work on all modal formulas, but it does work on modal formulas of a certain syntactic shape. And what it does is you input the modal formula that has the right syntactic shape, and it outputs the first order property that it corresponds to. So that's Salkvist's theorem. That's sort of the strongest theorem in correspondence theory. That's the algorithmic method that allows you to algorithmically determine which first order property corresponds to a certain type of modal formula. And a more general theorem, the so-called Goldblatt-Thomason theorem, this characterizes exactly which class of frames are first order definable. So if I give you a class of frames, so this is here we have this class of frames right here. So this is, here we have all frames, and I'm interested in this particular class right here. And I would like to know, is this class definable by some modal formula? So I'm assuming that this class of frame is already definable by a first order formula, but I want to know, is it also definable by a modal formula? So this first order definable class of frame is modally definable in the sense that there is a modal formula such that that modal formula exactly picks out this particular class of frames. So it's valid exactly on this class of frames if and only if it's closed under all of these nice conditions. And I don't have at all enough time to go through these right now. If you refer to this book, Modal Logic by Blackburn, De Rijke, and Venema, they will define what all of these properties are. If this was a class on general modal logic, I would go through each one of them. But I just wanted to point out that there are two very, very strong and beautiful theorems in correspondence theory: Salkvist's algorithm or Salkvist's theorem and the Goldblatt-Thomason theorem. Those are the two theorems. Goldblatt-Thomason tells you exactly which first order definable class of frames are in fact modally definable, so we know we can characterize that class precisely. And Salkvist's theorem gives you an algorithm that will automatically generate the first order correspondent to particular modal formulas. Okay, so that's just a very brief introduction to correspondence theory. As I sort of mentioned at the end, there's a lot more to it, and I encourage you to look at some of the books on modal logic that I've referred to. But if you have any questions, please contact me by email or ask me in class. Okay, see you soon.